Hello and welcome to the GeoDict 2022 workshop for digital rock physics. My name is Arne Jakob and today I'm going to guide you through this workshop where you learn how to import, segment and crop digital images of a standard reservoir rock. Execute your own absolute permeability simulation using the new features of GeoDict. Run a standard mercury intrusion capillary pressure curve simulation. Compute relative permeability of a drainage setup, and how to use the new forced imbibition capabilities in Zatodict. This workshop is pre-recorded. Nevertheless, please ask anything related to digital rock physics anytime by asking questions in the WebEx chat. Please note that all the shown structures and results will be available online from the DRP Workshops webpage. We have expanded the workshops team with our team leader Oliver, business manager Christian, myself and our software engineer Sven. So you will get highly qualified answers from math to market experts on any related topics. The workshop is split into 3 parts. In the first part, you will learn how to perform import and structure operations. Therefore, you will use the Artificial Intelligence or AI segmentation module on a gray value image stack of a Gildehauser sandstone. Then you will learn how to use the structure analysis capabilities of GeoDict to compute and visualize the pore connectivity within the sample. In the second part of this workshop, we will determine absolute permeability. I will also show you how to include the effects of microporosity on permeability in a sample. Finally, I will introduce a workflow to determine permeability of a whole rock core. In the third and last part of this workshop, I will show you different solutions offered by GeoDict of how to perform digital special core analysis. This will include a one-click MICP simulation, the modeling of a drainage setup with a related relative permeability computations, and the new forced imbibition capillary pressure geo app. Please note that between each part there will be a break to grab a coffee or ask questions. Traditional core analysis performed in laboratories is divided into routine and special core analysis. The routine core analysis is normally carried out on core plugs or whole cores. It comprises determination of porosity, grain size distribution, and absolute permeability amongst others. Special core analysis is far more detailed and assesses petrophysics, fluid properties, EOR, formation damage and rock mechanics. From the many lab workflows, we will look at capillary pressure curves and relative permeability. So, some of the workflows in core labs may be performed using digital core analysis. And during this workshop, we will perform some of these steps as digital core analysis with GeoDict 2022. In conventional laboratory analysis, the experiments may include different procedures which might have big time demands. Furthermore, you will also have the uncertainty of the applied experimental method and even the variation of results from different labs. While doing these lab experiments, it is often required to use expensive lab equipment. The digital core analysis offers new workflows, fast results, and data quality assessment. Where numerical analysis applies, you can use GeoDict to create reproducible results and to automate the workflow for your digital samples. That's why we will now focus on the GeoDict standard for digital core analysis. The standard comprises 3D image processing and segmentation, geometric characterization, computation of single-phase flow to obtain the absolute permeability, computation of two-phase flow to predict the capillary pressure curve and relative permeability, also for forced imbibition, the prediction of resistivity index based on a set of fluid distributions, the determination of mechanical properties, and also the computation of reactive flow considering the mineral dissolution and precipitation in a given amount of time based on individual geochemical systems. In this workshop, we focus on each of these features except mechanical properties and mineral dissolution. Nevertheless, Please contact us if you need further assistance for your individual project. In this session, you will learn how to create a multi-phase structure from a stack of gray value images. On this slide, the image stack is on the left side, while the segmented structure is on the right side. Visually spoken, we start with the raw gray value data of the image stack. We will segment, process, label, and visualize the 3D image of an outcrop of the Gildehauser sandstone, so that it looks similar to the structure visualized here on the right side. We have added all slides and working steps as PDF to our web page, so feel free to use them during or after this workshop for your own training purposes. Now, please open GeoDict 2022 and follow my steps. I will do the following training slowly, but if you get lost anyway, try using this PDF or the WebEx chat in order to catch up. What we want to do first in GeoDict 2022 is to check if our project folder is set right. To do that, you can right-click on the project folder and select project folder. Make sure that your project folder is My First GeoDict Project. Now we want to import the gray value image stack of the Gildehauser sandstone. To do so, please click Import and import GeoVol. In the Import GeoVol menu, please browse for the dataset. The dataset was provided by this workshop. To open the data stack, you have to enter the right dimension of the TIFF stack, which is in our case 890N3 for NX, 890N7 for NY, and 570 for NZ. You always have the possibility to crop in the import window. And as you can see, the corresponding file size changes. The data type of the image stack is integer. The voxel length is 4.4. To continue with the image processing, click Image Processing. In the 3D image processing window, slices in the main direction in X, Y, and Z are shown, as well as the corresponding gray value histogram. As you can see in the histogram, GeoDict already shows a threshold to distinguish between the phases pore and quartz. This was made by the Otzo filter, which is default in GeoDict 2022. By moving the visibility slider on the top, you can make the segmentation more or less visible on the gray value image stack. By clicking and holding the right mouse button, you can zoom and zoom out. And as you can see, the suggested segmentation is not as good as it could be. So what we want to do now is to create an AI segmentation. As you might have already noticed, the dataset is very large for this training purpose. So in order to reduce the memory demands, we want to crop our structure first. Please enter the corresponding values into GeoDict in the image processing and crop menu. This is 294 for X to 594 in N and Y direction. This is 93 to 393, and in NZ this is 270 to 570. When you zoom out, you can already see how our crop would look like. This is a yellow area. To apply the crop, please click Apply. Now our volume is much smaller. Please zoom in by clicking and holding the right mouse button and move the view so that you can see more of the XY slide. You can also adjust the gray value range or improve the contrast. Set 12,000 for the lower boundary. For the upper boundary, set 30,000. In GeoDict 2022, a variety of artificial intelligence or AI algorithms are available. In this workshop, we will use the AI segmentation to segment our gray value image stack into the faces, quads and pores. To do so, please open the image segmentation menu and open the AI segmentation tab, which are located here. First, pick the brush tool and define the corresponding regions by selecting the pores with the brush tool. But set the brush size to 4 and increase the visibility of the drawn label. Then you can select the pores by clicking and holding the left mouse button. Make sure to select regions from different slices. If you need more accuracy in the painting, select the tool for moving and zooming to zoom in. Now select Material 2, or the quartz grains, and do the same with the quartz grains. If you have selected a material you didn't want to select, you may erase that with the Erase tool. Please make sure that you've selected regions where you think that the algorithm might struggle with the segmentation. So in our case, this would be narrow pore throats. Now zoom out again and train the algorithm by clicking Train. As you can see, the grayed out preview is now available. So click Preview to preview the suggestion of the current segmentation. And zoom in. So what you can see is that the algorithm still struggles with the edges of the grains or the pores. So we have to improve our training by providing the algorithm more data. So go back to Label, View, and select the brush tool again for quartz. And remember the regions where the algorithm struggled. You might even choose a smaller brush size. Click Continue Training and preview the current segmentation. As you can see, the segmentation is now better, but it still struggles at the boundaries of the grains. So go back to Label View and train the regions. Click Continue Training and preview. As you can see, the segmentation is now almost perfect, but there are still some boundaries of the grains which are not segmented correctly. So make sure to select them too to provide the training data for the algorithm. If you are satisfied with the current segmentation, please click Create Segmentation. As soon as the computation is finished, Dudict opens the result viewer. In the result viewer, all the parameters are listed which were used for the segmentation. So, the general structure information, the constituent materials, or the different number of materials. In our case, this is pores and manual because we were not giving the material to a name yet. Then the volume fraction amount and the total runtime. Close the result viewer by clicking Close. You may also close the 3D image processing window. What you can see now in Dudict is the segmented structure in red with invisible pores and the corresponding volume field, which is in our case the gray value image stack. You can uncheck structure or volume field to make them visible or invisible. Slice through the structure by clicking and holding with the left mouse button the slice slider. Uncheck the volume field and check the structure to have a look at the structure only. We may now have a look and the Statistics tab. This gives you the total volume amount of each of the assigned phases. As we know ID 0 is pores, we know that we have a porosity of 20.14%. We may also display the volume fraction as voxel counts. Since we do not need our volume field of the gray values anymore, we can discard them by clicking Volume Field, Discard Volume Field. To do so, click with the right mouse button on Volume Fields and discard the Volume Field. As you can see, the Volume Field tab is now grayed out. In the next step, we visualize the structure in 3D. You can do this by changing the view from 2 to 3D in the toolbar. You can now click and hold the left mouse button to move the structure around. Now, please adjust the colors by selecting the color and visibility settings from the right toolbar. Set the color of the quartz grains to gray. You can also adjust the rendering type of the structure by selecting the Smooth Renderer from the Structure menu. Now the 3D representation looks much better. You can also visualize the pores alone by unchecking the visibility checkbox and checking the visibility of the pores. Please uncheck the pores visibility and check the visibility of the quartz again, because what we want to do now is to change the information of the materials. To do so, select the constituent materials from the toolbar and what you can see here for each material is a predefined solid, fluid, porous solid, or undefined phase. As we know, quartz is a solid, so we choose solid. And look for quartz in the material table. Select quartz and click OK. We want to do the same for the pores, so click Pore and choose Water. And as you can see, Geodict already inserted the solid density of the quartz, and for the water entered the fluid density, viscosity. Click Run to insert these parameters. And as you can see from the material information legend, we now have water in our pores and quartz as solid materials or grains. We now want to check the connectivity of the pores within the structure. To do so, please select the module Porodict from the toolbar and choose Open and Closed Porosity from the drop-down menu. As you can see, there is a variety of other calculations or simulations available. You may define the pore size distribution, identify pores, calculate the chord length distribution, and many more. For this workshop, select the Open and Closed Porosity and edit the options by clicking Edit. You want to check all these parameters, which means that the open and closed porosity will be determined over every side of the structure and assumes connectivity between voxels of the face, edge, or vertex of each voxel. Make sure that you have checked the checkbox for Write Open and Closed Pores as GDT file. This will make the open and closed pores available as structure. To start the calculation, click OK and run. As you can see, Geodict now opens a result viewer to display the result of the open and closed porosity calculation. In the report, you may have noticed that the overall porosity is the same as the porosity we already determined in the statistics menu. Then, as next entry, you can see the open porosity in percent and the closed porosity with a very low amount of 0.05%. Geodict also displays dead end and through pores, or performs a sub-classification on the pores. And as you can see, the amount of dead end porosity is very, very low, while the amount of through porosity with connectivity is almost our total porosity. You may now load the structure with open closed porosity from the Data Visualization tab. Close the result viewer by clicking Close. In the material legend, you now can see that a new material appeared. You can make this material visible by unchecking the visibility button of the quartz. Now, this is your total dead porosity or closed porosity. Now you can have a look at the volume fraction, and as you can see, for material ID 02 or the closed porosity, you can now see that the volume percentage is 0.05, which is the same as displayed in the result viewer. To look up the results again, select File, Open Results, and select the open and closed porosity GDR file. With Geodict, you can also calculate percolation paths. To calculate them, select Product again, and this time choose Percolation Path. What we want to do is to display the 10 largest flow paths to the structure. The material to analyze is our pore space. You may leave the boundary conditions as is, clicking OK to run the simulation. In the result viewer, the results of the 10 largest paths are displayed. You may visualize them by clicking Data Visualization and Load Result. Minimize the result viewer and have a look at the result. As you might have noticed, our closed porosity is still visualized. You may use this tool to determine the heterogeneity of the percolation within a structure. This might be very useful for tight rock structures. Now, please maximize the result viewer and load the original structure from which we have started the calculation by Load Structure. Click Yes to show the quartz grains again. As last action in this workshop, please change the structure information to Gilderhauser Sandstone Crop. Run. And now, to close this chapter of the workshop, please save your structure. You may leave that name or choose another one. Click Save to save the structure. We will now have a break where you can ask questions. Welcome back to the Digital Rock Physics workshop for Geodict 2022. In the second part of the routine core analysis workshop, we will focus on the computation of absolute permeability of your segmented Gildehauser sample. To do so, we will use the model FlowDict to compute the absolute permeability or the fluid flow field using the Navier-Stokes or Brinkmann equations. On the right-hand side, a 3D representation of the Gildehauser rock with its computed corresponding flow field is visualized. In GeoDict, important information about digital rock samples and the fluid flow behavior within the structure can be gathered. We can also consider the effect of microporosity on permeability. This is especially useful when the resolution is not sufficient to display the pores within a structure correctly. But I will also show you an example for that case later. Further applications are enhanced oil recovery, groundwater in aquifers, hydrogen storage, or CO2 sequestration. The solvers of GeoDict are well known for their performance and accuracy. In this workshop, we will use the Lear solver to compute the fluid flow. This applies an adaptive grid to the structure to enhance and improve the runtime. This reduces memory demands and the speed or convergency of the solver. Therefore, this enables us or you to compute the flow field of very large structures, for example 4000 voxels to the power of 3. But before we start our own simulation of the Gildehauser sandstone, just one word about the boundary conditions in flow direction. On this slide, the effect of the boundary conditions on permeability is displayed. As you can see, the permeability is artificially reduced by choosing the periodic boundary conditions without any inlet. This boundary condition is therefore not suitable for rocks and should not be chosen for these applications. You should either choose symmetric boundary conditions, which might need a little bit more memory, or the periodic boundary conditions, which are the default in GeoDict. But we do not have boundary conditions only in flow direction, but also in tangential direction. In this overview, the possible combinations of boundary conditions in flow and tangential direction which are suitable for rocks are displayed. In GeoDict, the default settings of FlowDict allow starting the computation of rock permeability right away without changing any of the boundary conditions. Nevertheless, you can manually choose the boundary condition which fits your setup best. To compute the fluid flow, please go back into GeoDict 2022. You might have closed your structure, and in case you have done so, you may also load your structure file by clicking File and Open Structure. Now you can reload the structure you already saved in the last part of the workshop. And as you can see, the original values for the volume statistics are maintained. Adjust the view to 3D rendering and choose the smooth structure renderer. As you know from the last part of the workshop, you may set the color visibility options here. But now we want to compute the fluid flow. To do so, please choose Predict in the Geodict toolbar and choose FlowDict. As we want to calculate absolute permeability as material property, we are using the Stokes-Brinkmann solver. The Brinkmann term is only applied when porous voxel are assigned. You may edit the solver options by clicking Edit. As you can see, the temperature is set to our default value of 20 degrees Celsius. Since we have changed the material properties of the pores, you can already see that water is chosen as a simulation fluid. But you can always edit these parameters in the Solver Options menu. And choose other fluids like oil, mercury, air, and so on. You may even define your own fluid by choosing the manual value, where you are able to set the fluid density and dynamic viscosity by yourself. You can now choose a different result file name for your Geodict result. Choose Stokes result Gildehauser.gdr. To edit the boundary condition options, please select Boundary Conditions from the Boundary Conditions tab. You can now choose the computation direction of the flow solver. As default, the Z direction is set. As I already mentioned, the default values of Geodict 2022 allow a correct estimation of the boundary conditions for digital rocks. So in flow direction, that would be periodic, with the implicit region for inflow and outflow. And in tangential direction, that would be periodic. In our example, we will simulate fluid flow determined by a pressure gradient, which is applied to the top and the bottom of our structure. In our case, that would be 0.02 Pascal. For some simulation setups, it might be necessary to adjust the slip length. The slip length refers to the pore solid boundary conditions, or the fluid flow velocity on the surface of the grains. Now we want to edit the solver options. Please choose Solver from the Solver tab, where to choose the Lear solver. As a stopping criterion, please choose an error bound of 0.01. As you can see in the tooltip, that would stop the solver if the relative difference of the predicted permeability or other chosen parameter within the last 100 iterations is smaller than the given threshold. parallelization, please choose your local maximum parallelization. But you may also edit the parallelization by clicking Edit. If you have stopped a previous calculation of the Lear solver, you may also restart from a GDR file. You can browse for the GDR file and choose it as input for your next flow calculation. You may leave these checkboxes for Analyze Geometry, where the solver checks if a flow path is available. You might also leave the right compressed volume fields, which is a nice feature to save disk space. And you want to use the multigrid method. This will improve the runtime of the solver. In GeoDict 2022, there will be also an option to choose the Krylov method as enabled, disabled, or automatic. Choosing automatic means that if the solver detects porosity below 15%, it will automatically use the Krylov feature. This feature improves the runtime for tight reservoir rocks. You may also leave the other speedup settings on default. To look up which equations and references GeoDict uses, just have a look at the Equations and References tab. And the citation of the references. To start the solver, click OK and run. During the calculation, you might also have a look at the current results of FlowDict, where the current permeability is listed and the accuracy, as well as the prediction. When the computation has finished, the result viewer of Flowdict opens again automatically. Have a look at the results by clicking Results and Report. You can now see the permeability tensor and the error bound tensor because we have chosen the error bound as stopping criterion. To change the permeability unit, you may change it from the permeability unit tab to millidarcy or darcy. Click Apply. Which yields the permeability tensor in millidarcy. You may also have a look at the plots of pressure and velocity distribution within the sample. Or displays the convergence. In Geodict, you may also create videos. To choose the parameters for the corresponding videos, click Edit Parameters. For the chosen video style, which is Flow Visualization Video on default, you can change the video duration here. Feel free to try this after the workshop. But now we want to load the Flow Visualization field. To do so, please click Flow Visualization. And since we only computed the Z direction, load the Z direction flow field. You can now choose which part of the fluid flow velocity you want to visualize. Since the fluid flow is direction dependent, you may choose only certain parts of the direction vector. For our case, deselect the velocities in x, y, and z, and only load the mean flow velocity field and the pressure field. Click OK. And close the result viewer. You may now have a look at the flow field only. So deselect the visibility of the structure. In the volume field menu, make the volume field only visible within the pores. So deselect the visibility of the flow field on the quartz grains. You may now enable transparency, which gives you a better impression of the 3D distribution of the flow field velocity. Click and hold the left mouse button to move the structure around. You may also have a look at the pressure field by choosing the pressure field from the menu. You may now enable the visibility for the structure again. And what you can do now is to clip some parts of the structure. To enhance the rendering quality, you might choose the global lighting. You might also want to enable the halos. Go back to the volume field view and choose the velocity field again. You may change every property of the visualization in the visualization menu on the right hand side. Click Data View, and there you can choose which part of the visualization you want to change. In our case, we want to change the values of the volume field. Set the transparency density to 0.85. Just play around with these values to get the best impression of the flow field. Now, let's just assume for a moment that your quartz is a porous material. You can choose that by selecting the constituent materials from the menu bar. There, choose the porous material from the material table and set it to manual. You are now enabled to enter a permeability for your material quartz. We now only had a look at the permeability tensor in Z direction, or the computation or simulation direction. To obtain the full permeability tensor with each direction, so X, Y, and Z, we would have to compute the fluid flow in these directions as well. So this means that you would need 3 independent calculations of flow. The permeability tensor of these 3 main directions displays the respective permeability for the whole rock core. In Flowdict, you may also visualize the fluid flow velocities in each direction separately. But to provide you with a real-life example, I have prepared an outcrop of an Stellaris carbonate rock. The microporosity is expressed by the Brinkmann term, together with the Stokes or Navier-Stokes equations. In this example, I would like to show how the fluid flow is computed, including the effects of microporosity in the Stellaris carbonate rock. As you can already see in the gray value images on the left side, the Stellaris rock has a lot of microporosity which should not be neglected in the computation of the fluid flow field. In this case, the workflow is similar to the previous one, but the microporous domains should be segmented as separate material, and the permeability of the microporous domain must be known. For example, you may obtain this by using other methods, like high-resolution FIB-SEM measurements. With this information, you can now define the permeability of the microporous regions and run your computation. When running a simulation on the Stellaris rock, you may define an exemplary permeability of 1 millidarcy for the porous domains. I have visualized the result of the Lear solver on the right-hand side of this slide. As you can see, the flow is not only computed in the pores, but also in material 1, which is the defined microporous domain. The resulting flow field also shows the lower fluid flow velocities in the microporous domains compared to the open pores. In FlowDict, you can also define the permeability of whole rock core samples. If you don't want to lose the information of a cylindrical pore sample, you can always calculate the fluid flow of the entire core plug. By doing so, you should differentiate between the void space outside of the plug and the pore space inside of the sample. Set the void space as solid material in GeoDict and start the computation of the fluid flow field. Since the permeability is computed over the area of the computational domain, one should remove the effect of the void voxels outside of the sample. This is as easy as shown here. Just look up the volume fraction of the flow cell material from the Statistics tab, calculate the core volume fraction as shown, and finally determine the core permeability. This means that you have to multiply the computed permeability of the whole domain with the number of all voxels divided by the number of gray voxels. We would now have some time for our second break, and of course, time to ask questions and have a cup of coffee. Welcome back to the third and last part of this workshop. The topic is digital special core analysis, or in other words, two-phase flow. First, we will compute a digital mercury intrusion capillary pressure, a digital MICP. Then we continue with a drainage computation, where we will have a look at the settings for computation of the relative permeability based on the result of our previous drainage computation. Finally, we will run the new forced imbibition capillary pressure GeoApp to predict a complete capillary pressure hysteresis cycle. In GeoDict 2022, we enable you to compute two-phase flow using the module SatGeoDict. While we introduced the dynamic pore morphology method with GeoDict 2021, we have developed the true contact angle method for GeoDict 2022, which extends two-phase flow capabilities to the entire contact angle range from 0 to 180 degrees. We've also invented a new GeoApp to enable you to compute forced imbibition setups. We introduce oil-wet materials with GeoDict 2022, which affects the contact angles of the fluid rock interface. We will start with performing a mercury intrusion capillary pressure simulation. Go back into your GeoDict and discard your volume fields first. And set the clipping of the structure to default again. You may also disable the global lighting and showing the halos. Now I want to show you how to perform your simulation. Go to GeoApp and choose ZGedict from the GeoApp menu. From the drop-down menu, please select the mercury intrusion capillary pressure. To edit the options, click Edit. In GeoDict 2022, you are also enabled to compute the Tomer model. The Tomer model accounts for the hidden porosity in your dataset. Run the simulation by clicking Run. After the simulation is finished, you might want to have a look at the result viewer. As you can see, as hidden porosity 1.21 is considered to be hidden in our dataset. You may also have a look at each of the saturation steps individually based on the applied pressure. This gives you the saturation of the non-wetting phase, which is in our case the mercury, and the wetting phase, which is air, and the corresponding capillary pressure and calculated mean curvature. Select Plots to have a look at the complete pressure over saturation plot. As you can see, the Tomer model accounts for the hidden porosity and shows you the area of the hidden porosity within your sample. You may change the reference volume from the pore space volume, which is seen by your scan, to the modeled pore space, which includes the hidden porosity. Click Apply to set these values to the plot. To give you an estimation of how well the Tomer model works, I have prepared a small plot where you can see the MICP results of Berg et al. 2016 compared with the MICP simulation of GeoDict with Tomer model enabled. And as you can see, the curves of the saturation are almost identical. The result viewer of the MICP Geo app also enables you to visualize your saturation steps. So, for each pressure step, there is a saturation GDT file, which can be loaded by Geodict. Let's choose one in between and load the corresponding GDT file. As you can see, the sample is almost fully saturated here. Go back to the Color and Visibility menu and disable the visibility of quartz. You may also visualize these parts of the structure which are not already saturated by mercury. Uncheck the visibility for mercury so that you can see the remaining porosity of the unsaturated pore space. To perform the next drainage simulation, please maximize the result viewer and load the original structure. Close the result viewer of the MICP Geo app. And uncheck the visibility of the pores. Now I would like you to perform a primary drainage computation using Satudict. Choose Satudict from the Predict menu and choose Capillary Pressure Curve from the drop-down menu. Click Edit to edit the solver options. In the capillary pressure wetting parameters table, set up the parameters. As experiment, choose drainage, which is already set by default. Check the replaced fluid can leave a residual checkbox and leave the other parameters on default. Change your result file name from MICP result to drainage result. To have a look at the included constituent materials, select Constituent Materials from the tab. In Geodict 2022, you are enabled to use the True Contact Angle method. The True Contact Angle method extends the contact angle range which is possible for the materials from 0 to 180. As interfacial or surface tension, please insert 0.03. As we don't want to have mercury, choose oil from the material table as invading fluid. As you can see, I can only choose air as replaced fluid. That is because I have air chosen as constituent material in my structure. You may change that by making the rock fully vacuum-saturated, by checking water in the material table for the open porosity and the closed porosity. Now look up the contact angles, which are used by Satudict. For the wetting phase, which is in our case water, we assume a contact angle of 40 degrees. For the non-wetting phase, which is in our case oil, we assume a contact angle of 140 for the quartz. Now let's set up the boundary conditions. To do so, choose Boundary Conditions from the Boundary Conditions tab. As we want to let the oil invade only from one side, check the checkboxes for the wetting reservoir on each of the sides of the samples except one in Z direction. There would be the non-wetting phase reservoir, which means in our case the oil reservoir. Now select the Solver Parameters tab. You can leave the step size on 1, since we have a very small structure. For larger structures, please select higher values to get a faster result. We want to write the steps to GDT for every one of the pressure saturation. As neighborhood mode, which means when a voxel is connected to the next, select face, edge or vertex, which basically means that there is a connection when a voxel touches another voxel. But now you can start by clicking OK and run. You may now have a look at the result viewer, where you can see the saturation of the wetting phase and the non-wetting phase for each pressure step. For each phase, you can look up the saturation plot and by selecting another phase, the corresponding saturation. As well as in the MICP app, you may visualize the results by creating videos or loading the GDT structure file at a certain pressure step. You can get to change the saturation unit from relative to absolute. And also change the reference volume if you have computed the Tumor model as well, or if you want to compare it to your total sample volume. Now, let's have a look how the relative permeability of each of the saturation steps would look like. Choose Relative Permeability from the already opened SatuDict menu and edit the solver options. You may now choose our former created drainage GDR and calculate the pressure step, the permeability of each of the chosen saturation steps. You may increase the number of relative permeability calculations but for this workshop, please leave it on 6 FlowDict calculations. We want to calculate the relative permeability for each of the phases, so select the wetting phase as well. But let's have a look at the other solver options as well. You don't have to change anything up to here. In the boundary conditions, you may set up the computation direction of FlowDict, as well as the boundary conditions in flow direction. In the solver menu, you might not want to use the simple FFT solver, but the Lear solver. To get faster result, you might this time choose a higher error bound of 0.05 or even higher. You know these settings already when we've used FlowDict to calculate the absolute permeability. Click OK and run your relative permeability simulation by clicking Run. As you might have noticed, the permeability calculations might take a while for each of the saturation steps you've chosen in the input menu. Let's have a look at results. So, for each chosen saturation of the wetting phase, you now have corresponding relative permeability. Since we only computed the permeability in Z direction, we only have the permeability values in Z. This would be the permeability in X direction, Y direction, and Z direction. But let's have a look at the plots. You can now see the relative permeability of a saturation plot here. You can choose the graph type, the phase, and the permeability unit from relative to effective, and the saturation unit from absolute to relative as well. You also have the possibility to visualize the data of each saturation step by loading the GDT from the data visualization window. Finally, and as last point on our list for today, is the forced imbibition simulation in GeoDict 2022. This means that we have extended the pore morphology method in GeoDict 2022 to consider mixed wettability as well. This means that we can simulate alternating cycles of drainage and imbibition, compute both spontaneous and forced drainage, and of course, compute the relative permeability and the resistivity index. This means that in GeoDict 2022, you are now enabled to simulate the full hysteresis cycle. First of all, what is forced imbibition and what are the requirements to simulate forced imbibition? First of all, forced imbibition follows a spontaneous imbibition, where the water pressure is higher than the oil pressure. It is equivalent more or less to the porous plate or centrifugal experiment setup. In a simulation environment, that means that we require both water-wet and oil-wet regions in GeoDict. Therefore, forced imbibition can be understood as drainage, since the curvature of the oil-water interface changes its sign. But before starting the simulation in GeoDict, I want to have a word on introducing the oil-wet materials in GeoDict. Oil rock contacts are transformed into individual oil-wet materials. These are, however, limited by the presence of large pores and the corresponding volume of pore space considered, which can be chosen in the menu of the GeoApp for the forced imbibition. Now, as last part of the workshop, we want to run a forced imbibition simulation. To do so, please select GeoApp and SatuDict. From the drop-down menu, you may choose forced imbibition capillary pressure. Edit the options by clicking Edit and have a look at the graphical user interface of the input parameters of the forced imbibition GeoApp. In the GeoApp, you may choose a fluid for the wetting phase and for the non-wetting phase. Since we want to start with a primary drainage, we want to have water which fully saturates our rock and is then replaced by oil. Leave the surface tension on default. And now, in case you may have different material IDs or different solid material IDs, you may choose different contact angle for each material in your structure. Since we only have in quartz a solid material in our structure, only the contact angle for material ID 1 will affect the results. Since the forced imbibition GeoApp also consider mixed wettability, you can set an oil wet contact angle for your material ID 1. You may limit the oil wet surfaces to large pores by choosing a different value for the volume of pore space considered percentage. As you can see in the tooltip, more contact material changes and increased saturation change during forced imbibition, but decreased saturation changes during spontaneous imbibition. You may change the fluid interface step size from 32 to 1. Leave the spontaneous force transition mode to sequential. And choose primary drainage as your start of the hysteresis cycle. And end the hysteresis cycle with forced imbibition. At this point, you may try non-monotonic pressure after your workshop, or even compute the relative permeability for the combined imbibition process. Leave the result file name on forced imbibition result, click OK, and run. As soon as the solver is finished, have a look at the main results of the forced imbibition GeoApp. As you know, we started with our primary drainage, followed by a spontaneous imbibition, which ends with a forced imbibition. You also have irreducible water saturation left in your sample, as well as a residual of oil saturation. Let's have a look at the plots. As you can see, you have your primary drainage colored in red, followed by your imbibition, or spontaneous imbibition. As soon as the pressure becomes negative, you know that you're in the forced imbibition domain. You may adjust the plot settings by right-clicking in the plot. Uncheck the box for scale access automatically and insert your own values of 20,000 to plus 20,000. Click Apply to apply the changes you've made. The irreducible water saturation is colored as blue here in this region to the left of the plot, as well as a residual oil saturation to the right. Close the result viewer by clicking Close. Now we want to load the mixed wet structure, which was created by the Forced Imbibition Geo app. To do so, select File, Open Structure, browse to your Forced Imbibition result folder, and load the mixed wet geometry for imbibition. You can now uncheck the visibility of your structure, of your oil, to have the mixed wettability visualized in GeoDict. In this case, we've only visualized the oil-wet surfaces. Have a look at them in 2D. And check the visibility box for the quartz grains. Finally, I want to sum up the new features which were discussed in this workshop of GeoDict 2022. For Flowdict, this would be the increased efficiency by the implementation of the Krylov method. This method reduces the runtime of Lear in narrow pore throats and microporous regions. Satudict is now able to predict unresolved porosity via Tomer modeling. Using the forced imbibition script, we also consider mixed wettability in spontaneous and forced imbibition. By developing the true contact angle method, we also improved the contact angle range from 0 to 180 in GeoDict 2022. Thank you for your attention during this workshop. Please notice that there are several talks in the other business areas as well. That's it for our workshop on digital core analysis with GeoDict 2022. I hope you've enjoyed the workshop and want to test more GeoDict features with the remaining time of your workshop license. Of course, there's still a lot more to discover. We still have time for some questions, so feel free to ask any of yours now.